Okay, so now we will start talking about oxygen consumption. So we'll share this talk between Dominique Lefevre, working at the Mediteranean Institute of Oceanography in France, and myself, Matthieu Bressac, working in the Laboratoire Oceanography Villefranche in France as well. Okay, so we will start by giving you a brief overview of the processes controlling the oxygen distribution in the mesopelagic. We will talk as well about the actor of this mesopelagic respiration and the controlling factors. Then we will introduce and discuss a few different methods to measure the dissolved oxygen concentration in seawater. And in a third section, we'll talk about process studies, so give you some insight, some describing in vitro and in situ incubation. And at the end of this talk, we will explain and talk about the way we can relate oxygen consumption measurements with the carbon cycle. I will let Dominique start the introduction.
So first, we will give a brief presentation of what we define as a respiration. So respiration is happening in a cell at the level of the respiratory chain, feeding up.
But if you use your mouse,
Yes, I use the mouse.
yes, the online participants can see that as well.
So using up organic substrate to feed the respiratory chain, on that is oxidizing the organic matter using oxygen producing water. On the energy through the electron flow in the respiratory chain is transferred to the carbon to the Krebs cycle. Sorry, all this energy is transferred there to decarboxylate the organic matter and produce CO2. And one very important outcome of this two-step process is the respiratory quotient converting produced CO2 against oxygen consumed. So that's our working hypothesis or definition for respiration. Here, what we're going to present is at the global scale, what are the processes shaping the profile of oxygen in the water column. So the most important one is the physics on the interaction between the ocean and the atmosphere through the action and equilibrium of partial pressure between the atmospheric and the oxygen and the water. You got also introduction of bubbles and all that under the turbulence and the effect of the mechanism on the wind. Within the water column, when you got the surface water, you got the atmosphere, you got mixing in a mixed layer, or you got advection of water masses deeper in a water column, or you got convection to the bottom of the ocean, ventilating the different level of the water masses on the different level of the water, bringing down the oxygen. The other process affecting the oxygen concentration at the surface, you got photosynthesis and you got production. And the net community production is setting the level of oxygen through the biology available to the mixed layer. And then you got under the mixed layer processes, you got respiration and polymerization affecting the oxygen content using the organic matter through particles of dissolved organic matter, and you can follow that on isopycnal surfaces. And also, during the sedimentation of particles from the surface to the bottom of the ocean, you got degradation of organic matter, and that is using up oxygen for polymerization and respiration. So these are the processes happening on the whole water column and shaping what you see on the left, the oxygen profile through the depth. And that, depending on the ocean, they got different shape and profile. But usually what you got, it's organization happening under the mixed layer, and you see lower oxygen levels in the intermediate waters. bottom water, usually they are under the influence of ventilation, therefore they got more oxygen.
So, who are the main actors of the mesopelagic respiration? So this week, during this training course, we will focus only on free-living prokaryotes and particle-attached microbes. They are a key contributor of this mesopelagic respiration. Note that the particle-attached community include both prokaryotes, but also heterotrophic nanoflagellates and ciliates. And larger organisms like zooplankton and fish are also a key player for the mesopelagic evolution. So what do we know about the dynamic and microbial community structure in the mesopelagic? First, I would like to say that our understanding has been greatly improved recently thanks to new sequencing technology and metagenomic analysis. Here, I just want to highlight two recent studies showing first that now it is admitted that particles, thinking particles are largely colonized in the mixed layer. But once they leave this mixed layer, this aphotic zone, we have a rapid exchange between free-living prokaryotes and communities associated with non- and fast-thinking particles. So on this drawing, we can see that in the aphotic layer, we have the interaction are bidirectional. So the exchange between fast thinking and non-thinking and with the free-living prokaryotes occurs. But once the particles leave this aphotic layer and start thinking in the water column, going deeper in the water column, the interaction are unidirectional. So we have only an exchange from the fast thinking particles to the free-living pool or suspended pool. One of the consequences is that the species richness in fast thinking particles tend to decrease with depth, and at the opposite, it tends to increase with depth for the non-thinking pool. A second aspect is at the scale of the particles, we have rapid ecological succession, especially between primary degraders and secondary consumers. And this succession are driven by ecological interactions such as competition, predation, and by the change in the quality of the substrate and changes in temperature and pressure. So this is not exhaustive, but it's just to highlight the recent findings about the structure and dynamic of the microbial community in the mesopelagic. Right.
So here we are going to present one of the controlling factors, temperature. You've seen the previous talk on just now. It's one of the most important factors controlling respiration. So here's a quick definition on enzyme activities. You've got three properties defining the kinetic reactions. So it's an enzyme activity. It's the three cardinal temperatures, which is the minimum temperature at which temperature there is no process, but the thing is still alive. The optimum temperature, where you got the maximum activity, and the maximum cardinal temperature, where you degrade the protein, so there is no more activities on the cell is dead. So if you go any further, there is no more activities. From the optimum to the minimum, it's a reverse process, whereas between the optimum and maximum, it's not necessarily a reverse process. Okay, the first one to have presented the temperature effect on enzymes is Mr. Arrhenius, a Swedish scientist. And he defined the law relating the activity by the energy activity, EA, to the temperature, to the kinetic rate, K. So that's a law linking the two. And you can see an example here linking the apparent oxygen utilization rates to the temperature here in Kelvin. And according to Arrhenius, the relation between, I go back, between the minimum temperature and the optimum temperature, it can be represented as a linear process if you go on a log scale for temperature on the activity rate. Here we go. Sorry, mixing up. And if you use that relation, you can, with the linear relationship between the log of the activity and the inverse of the absolute temperature, you can derive the activity of activation, the energy of activation for the enzyme, therefore the Q10, which is the ability to react to temperature changes. With that Q10. So this is a kind of example of what we are used to use in the lab or on the ship to carry out a temperature experiment. When you do incubation with a gradient block in aluminium, you put your samples, whatever it is, and could be by production, it can be oxygen bottles, and you make a gradient between the low and cold, and therefore you can have a range of temperature for your measurative illustration. And from this, you derive a Q10 value. So I said you put your respiration rates against the inverse of temperature, and you derive a Q10 values using this expression. So from the slope, you get Q10 values. So this is an example of a Q10 of 10. Usually in literature or in models, Q10 values for ecology are usually 2. But as we mentioned, it's a very important value to constrain for respiration. And this is an illustration of previous result we had using this kind of approach for respiration. So what you got on the right panel, it's an experiment carried out on coastal waters, which is temperate waters. So that means the community is experiencing a large range of variation for temperature. What you got, if you look at the community respiration, it's very high Q10, above around 4. On this, on the gray, you got the one for photosynthesis, but for temperature for Q10. You can see the Q10 values for respiration is higher than the one for photosynthesis. So if you increase the temperature, you privilege respiration rates. So the heterotrophy compared to the autotrophy. Whereas when you are on a stable temperature environment, here it's in the Antarctic, sorry, you got the same variation between the same distribution for the Q10 value for photosynthesis and for respiration. And the mode of this distribution is 2, whereas the 2 modes are 2 and 4. You get the same mode. You don't favor, you don't influence the same way photosynthesis and respiration. So, how do we measure respiration? What's the tool we got available? The original technique, the most robust and still used reference method is Mr. Winkler, which is a Hungarian guy. And that guy used to work for a boiler company. And his boss asked him to derive a method to measure oxygen to constrain the corrosion into the water tank. So, this chemist is still provided the only available reference technique for oxygen with wet chemistry, which we are still using it today. And this is one example of the system we are using to do oxygen titration by colorimetry with different systems that is 30 years old. This one is a new device done in the lab in Marseille. And you will use in Ravi's lab same colorimetric system, but a bit more neat, available by a company. So this is what we spend our life on when we do wet chemistry with Winkler to measure that. So I will go through, I'm sure you all know the chemistry of Winkler, but we'll go through quickly on the chemistry of this one. So it does work. You get a water sample in which you use reagent 1 is manganese, and this manganese is going to be complex with the oxygen in the water when you put it in a basic environment, and you form a precipitate. And when you are in a basic environment, when you're using sodium hydroxide, we add up at the same time some iodine, and say it properly. So it provides the yellow color. And in the basic state, that iodide is complex and settled into the bottle. And to do the titration, you dissolve the precipitate by using acid, and you titrate the iodide with a thiosulfate. So that is the photochrometric method, which is shown on the picture. And you titrate the iodide, and it's proportional to the amount of oxygen that has been complexed by the manganese. So basically, you got 4 mole of thiosulfate for 1 mole of oxygen with the stoichiometry of that reaction. So it's a very easy method, but there is a kind of error sources that you have to be aware of this errors you are making. Iodide, if it's in acid environment, it's very volatile. So if you do a titration with an open bottle, you may lose some of the iodide, so therefore you do an underestimation of your oxygen. I mean, when you are using a stirrer, if you've got a huge vortex, then therefore you're inducing an error. You got a large error depending on how careful you are adding your reagents. So be sure your pipettes have no bubbles, and the volume added is correct, carefully checked. That's very important. And all the volume of reagent are in the bottle, not outside. I've seen it before. You have to constrain the consumption of iodide by the impurity of the reagent. That means you have to be careful on which reagent you are buying. So this within the community, we got a set of reagents we are avoiding from some companies because we know they are not reliable and provide impurities and therefore not accurate measurements. And you got oxidation of iodine in the air. Also, when you fix your samples, temperature control is important because temperature variation can alter the oxygen content on the iodine. And also, which is very important, always scale up your errors. And when I said don't add bubbles to your system, a bubble on the pipette is 50 microliters, 50 cubic millimeters. And that is 1.5 micromoles of oxygen. So therefore, you can have an error of 4 macromole on your final concentration. So when I say it's important, if you want to do a respiration rate, which is below the unit of macromole per day, if you add up a bubble, finished. You measure whatever you like, but not respiration. So that is very important. So a lot of care has to be done on that you're going to practice it during this week. Very important. Also, one thing you have to be very aware, since we are doing the titration in the bottle itself, a lot of care has to be done on the bottle calibration, the volume determination. That is very important. All our oxygen bottles are paired with the stopper, and a lot of care has to be put into cleaning the bottles and taking care the stoppers are not chipped, because that alters the volume. Therefore, you make an error, and we want to have precision on the oxygen concentration, which is precise to be sure it's 1 order of magnitude lower than the rate we're seeking for. So we can make abstraction of this water problems, of the volume problems. So you can see an error of 50 milligrams because we measure the volume by gravimetry, by weighing the bottle, empty and full. An error of 50 milligrams, which is not much. It's an error of 0.15 macromolars into oxygen concentration. And that's one thing you have to be always aware, scale up your errors. Be sure what you can, be very careful, you have to be very careful on something you got a degree of freedom. Okay, so if you are seeking a respiration of 0.5 and you got an error of 0.2 on your volumes, done. Goodbye. I won't trust your results. Also, something you have to take care of is the temperature at which you are fixing your oxygen in the bottle. So depending on the area you are in the ocean, if you are in the Med Sea, it's not that important because you're collecting sample between 13 to 25 degrees. So the effect of volume is not that huge. But if you're in the tropics and collecting samples at from the surface, which is 25 degrees, collecting water at 2 degrees on at depth, then you got a significant error on your volume when you pickle your sample. So you have to take care of that. But as a matter of habit, I invite you to take temperature as all time, wherever you are, because that is a kind of checking where your sample is coming from. So if there is happening with a blisking sampling, which happens, you got some grounds to say, yes, there is a problem because the temperature is not right. And if you got deep water at 20 degrees, you can question yourself. And that is kind of a live measurement, so therefore you can interact with the people. And then you cross-check with the nutrients people to be sure where your water is coming from. So it's a good habit to take temperature, 1 to correct, and 2 to keep track of your sampling. So now I'm going to move on to another method to measure oxygen. It's using the mass spectrometry, but it's more for dedicated to surface water, and dedicated to measure net community production. So we use mass spectrometry to measure the ratio between oxygen and argon. So we are based on one of the processes we talked about, equilibrium between the atmosphere and on the ocean. And to be sure, that method allows us to deconvolute the signal coming from the physics to the one compared to the one coming from biology. And we can do that because oxygen and argon, they got relatively the same properties, thermodynamical properties. So therefore, when you do the ratio of two, and also I forgot to say, the oxygen, as we know, it's a very versatile molecule, interacting with physics, interacting with biology. Whereas the argon, it's interacting only with physics. So when you do the ratio of both, you remove, in bracket, the physics. I'm being very careful. So and therefore, when you do this ratio, you got an estimate of a good proxy of the net community production within the mixed layer. So the way it works, it's that methodology developed by Nicolas Cassar in the University of North Carolina, using the IMS method, which is a incubator inlet mass spectrometer. Basically, you are collecting water from the underway on the ship. When you use an incubator, which is that little thing, which is a huge surface of material, equilibrating the water phase with the atmospheric phase. And with that large surface, you got the gas, equilibrated gas going to the mass spec. So that's the beauty of that thing. It's these filters, these little modules on linked to the water flow of the underway. And from that, you got the gas going to the mass spec, and the dynamic of that ratio provides net community production. So that's very easy to deploy at sea on the ship, and it's a very low maintenance. It's an hour maintenance a day, so you can do large mapping. So I'm going to in detail of how we deconvolute these fluxes, these biological fluxes, and using this ratio. So I'll go straight into the options. So I forgot to say, there's few assumptions in there. It's measuring the equilibrium between the ratio between oxygen and argon in the mixed layer. And you're assuming there is no exchange with the mixed layer. That means this upper mixed layer is one body, so 0D system, and there is no one interacting with it other than the surface and the atmosphere. That's very important. So that's the way we handle the measurements, and we do oxygen argon measurements, and we do air calibration once in a while, every 4 hours or something like that, for a little period of 10, 15 minutes to check up the drift of the mass spec. And then we bring in situ temperature, wind, salinity, to have the derivative variables, and that is fed into the algorithm to derive net community production. So it's an illustration of the raw signals, where you got here the oxygen to argon ratio in blue, that is the underway system of water. And what you got in orange is the air reference. And you can see during the life of the time series, you got a large drift of this reference. And that is used to settle the in situ water system. So that is to control the mass spec itself, in fact, on all anything happen. So you use that the drift, up you feed the system, and from that you correct your oxygen argon value to have variable net community production rates. So this is an illustration in some Antarctic, offshore Tasmania, going through the different polar front, tropical front and polar front, and you see the distribution of net community production along the gradient and through the front with maximum values on the tropical front. That's just an illustration. But with this kind of mapping, you can map the whole ocean. As long as you can fit that on a ship, which can be an oceanographical ship, but it can be another community ship or whatever. And that's another illustration. It's a study we did in the Med Sea during winter correction. And what's very interesting is the interpretation of your signal. So here, what you got is a map of the chlorophyll, surface chlorophyll, where you got in red the maximum chlorophyll zone of productions. And that is highlighted here by a positive signal of net community production. Okay, so that's normal, that's fine. And if you look at here, you got from what net community production derived from oxygen argon ratio tell you, it's heterotrophic because it's a negative flux. But if you look where the water comes from, it's where the water, the convection area. And in fact, the surface water is mixed with deeper water with deficit in oxygen in it. So it's not net community production, it's a mix of water from the surface with the bottom water. So you have to be very careful of the physics on the water masses mixing before interpreting your oxygen argon values. Okay, so you have to be sure you constrain your landscape. Okay, so now we move to sensors.
Yeah,
back to Matthieu.
Last tool. So oxygen sensor. We have two main types of oxygen sensors. Electrochemical and optical sensors. So in an electrochemical sensor, the oxygen molecule permeates through the sensor membranes and undergoes a chemical reduction reaction. And this reaction produces an electrical signal that is proportional to your dissolved oxygen concentration in your sample. But these measurements, one of the consequences of these measurements is that the oxygen gets consumed. And at the opposite with the optical sensor, so it's based on the principle of luminescence quenching by the oxygen. And in this case, for this kind of measurements, we don't have any consumption of oxygen. So it's one of the main difference between these two different techniques. The other difference is for electrochemical sensors, they tend to have a faster response time compared to optical sensor, but a shorter lifetime. And they tend to lift more than optical sensor, meaning that you will have to calibrate them more often. So depending on your application, what we want to do, you will choose one or another type of sensor. For instance, if you want to perform an in vitro incubation with rapid change in dissolved oxygen concentration, you will probably have to use an electrochemical sensor. And at the opposite, if you want to do long-term in situ measurements, it would be better to use an optical sensor. I will so briefly describe each techniques. First, for the galvanic oxygen sensor, one of the characteristics of the sensor is you have a difference in potential between the anode and the cathode. So both the anode and cathode are submerged in an electrolyte. The oxygen so diffuse across this membrane, and the cathode accept electron from the anode and pass them onto the oxygen molecules. So the anode is oxidized and the oxygen is reduced and consumed so at the surface of the cathode. And this reaction produces an electric current that is directly related to the dissolved oxygen concentration in your sample or in the ambient seawater. So one of the characteristics of this galvanic oxygen sensor is that they are self-polarizing due to the material characteristic of the cathode and the anode. And this is one of the main differences with polarographic oxygen sensor. So the principle is the same, except so that they are not self-polarizing, and a constant current voltage has to be applied between the cathode and the anode for this technique. One of the consequences is that for this sensor you have a warm-up time, a few minutes before we are able to do measurements. Just to note that this is the technique used by the seabird sensors that we use on CTD. And the last method, so the oxygen sensors, they are based on this principle of luminescence quenching. So it's the ability of certain molecules to influence the fluorescence of other molecules. So in this case, the oxygen is able to influence the fluorescence of a luminophore. So in the sensing foil, you have a luminophore. They absorb a photon emitted by the sensor, and they get an excited state. And in presence of oxygen, the luminophore will transfer this energy to the oxygen. And one of the consequences is that less photon will be emitted from the luminophore, and the amount of light that is returned to the sensor, that is returned at the photodiode, will be decreased, and this decreasing photon light will depend on the oxygen concentration. So this table is just to illustrate this table reports some characteristics of Andera oxygen octodes, different models. The numbers are not important here. I just want to illustrate three important parameters. Precision, accuracy, and response time that can be useful if you want to choose a sensor. So basically, the precision is how close your measurements are from each other. The accuracy is how close the measurements are to the true concentration. So here we have two illustrations. On the left, you have a low accuracy. You are far from your target concentration, and you have as well a low precision because each measurement are far from each other. On the right, you have a low accuracy because you are far from your target concentration, the true concentration, but your precision is quite good because all measurements are quite close from each other. And the last parameter that can be important, especially for profiling application and when you want to do some measurements in dynamic system, is the response time, which is the ability to respond to changes in dissolved oxygen concentration. And this parameter, the response time, will mainly depend on temperature and on the foil characteristics of your octode. So once you get some in situ measurements or measurement during your incubation, you will have to correct your concentration for temperature, salinity, and pressure effects on quenching. So this is the step you have to follow to do this correction. I won't detail them. Everything is explained on a book developed by the Argo community. We will put this document on the Google Drive. And they explain all the steps and they provide all the equations that we will have to use. Something important to notice is to correct the measurements to get your final concentration, you will have to use pressure, temperature, salinity measurements from a CTD. So if you do in situ incubation, for example, it's good to have a CTD test at the same time at the same place. So now we are done with the method. We will talk about process studies, in vitro, in situ incubation. So before starting, once again, a good cookbook providing the best practices for this kind of incubation. So this document will be on the Google Drive as well. So let's start with the in vitro incubation. So why do we need in vitro incubation? We have few advantages to, a lot of advantages with this kind of incubation. The main one, I think, is that it's the best tool to test or investigate the effects of environmental, biogeochemical, or ecological factors. Here on the right, for example, you have the plot published by Morten Iversen a few years ago. And so they did some incubation at two temperature conditions at 4 and 15 degrees. And they followed with time the evolution of the carbon-specific degradation rates. It's something that you can't do in situ, and you have to use in vitro incubation to do that. The second advantage, it's quite easy to set up compared to in situ approaches. 3 examples of bottle incubator, bottle incubation. Here on the left, you have a glass bottle equipped with an Andera oxygen octode, mounted from the top. In the middle, you have this luminescence measuring oxygen sensor. It's a sensor used to measure oxygen at nanomolar concentration, mounted on a glass bottle as well. And on the right, you have these presence spots that you can glue inside your incubator bottle, and then you can measure your oxygen concentration during your incubation through the wall of the bottle. So it's relatively easy to do the measurements and easy to set up. Then you have obviously some important limitations. The first one is that usually you need relatively long incubation, and you will have at some point well-known bottle effects, inducing a change in microbial community structure with the development of opportunistic microorganisms, probably a change in biomass and rates. And an important limitation as well, especially if you work with isopelagic sample, is this depressurization effect. So basically, you work at atmospheric pressure conditions. And it has recently been shown, a recent paper from Amano and collaborators, they show that working at atmospheric pressure can strongly increase your metabolic rates that you measure compared if you do some in situ measurements. And deeper are your sample, we tested the difference, the effects. Some challenge as well. One important aspect is to maintain in situ oxygen concentration. So if you work, especially if you work in minimum oxygen minimum zone, but you have to, when you sample your water, if you have to process it, for example, to remove swimmer, use a mesh, etc., when you want to analyze your sample, it's crucial to maintain in situ oxygen concentration, and it can be tricky. For bottle experiment, you will have to choose the material. Glass bottles are obviously the best material, but sometimes you will prefer use polymers because they can be more robust or for other reason. Here you have a study showing the gas permeability of different type of plastic. So these plastics, they release oxygen, they dissolve oxygen, and probably as well dissolve organic carbon, so that you can change the rate, your metabolic rates. So here you have an idea of the gas permeability of different type of oxygen. So nylon and acetyl are probably the best plastic that you can use for this kind of incubation, and polycarbonate and Teflon, they release a lot of oxygen. So one way to avoid this effect is to precondition your bottle by soaking your bottle in seawater with similar temperature and dissolved oxygen concentration, and use many controls to check for non-biological oxygen drift. And another aspect is to steer, especially if you want to incubate particles, is to steer your bottle, your sample. A recent study showed the importance of breakdown products around the particles that compete for enzymatic activity, so decreasing degradation rate. So if you remove this product by steering your sample, should have a more realistic rate. So Dominique,
okay. So it's old-fashioned way of doing community respiration. So this is when we use the Winkler method on fill up little bottles. So that's an exercise you will do, and it's fun. So what you do on water assumptions, you collect samples and replicates in little oxygen bottles, and incubate them for 24 hours. And the assumption is bottle incubated in the light provide net community production, which is production minus respiration. And the one in the dark are measuring respiration. So it's dark community respiration. And from this kind of incubation, very quick. Okay. So from this kind of incubation, you can get a vertical profile of broad primary. Fast? Sorry. From that, you can get a gross community production profile, net community production, and respiration through the water column. This technique is very nice. It's very robust for mixed layer and lymphatic layer. But if you want to measure up respiration in the deeper layer where the rates are lower, it's not the right technique, not the right resolution. And also, this, despite very nice, it's very time consuming. Because if you want to do a profile, you end up with 100 something 20 bottles, 5 minutes per bottle for the calibration, and you have to have your bottle ready for the next day. So, good luck. We've all done it. It's fun, it's reliable, but it's not the best tool. So, and why we are using now sensors deployed on different platforms, either mobile platform, like gliders, argo floats, or fixed moorings, or little toys we develop in different labs dedicated to surface layer to measure respiration and photosynthesis by the colleagues in Woodsoul. This is a system for in situ vital primary production, and also there is a thing we develop ourselves, the radar and the respirator. So here I'm going to talk of the tool of the radar. It's a homemade device, tricky to develop when you want to do tools yourself. And to jump on what Matthieu said about the material, the first generation of iodine was made with a chamber of 5 liters, but in plastic. Unfortunately, I didn't do physics of material when I was a kid, and I didn't know the plastic was transparent to oxygen and was a storage of oxygen. Basically, a plastic like polycarbonate is 6 times the concentration of oxygen than in seawater. So if you use a micromole of oxygen like bacterial respiration or whatever inside, the plastic, give it back. So basically, you can't measure anything. Wrong material to use in a in situ incubator. And you can try to precondition the plastic and everything, but it takes more than 6 months. So maybe on the small thing, but it's a long time. So this device, it's this.
I think it's up there.
Are we sharing?
Maybe something about when you maximize the
Sorry.
window.
I jump from one window to the other. Sorry. Sorry about that. The excitement. Okay, so this little device is got different things. So chamber, 5 liters, which is here in borosilicate.
Don't use the mouse.
So the chamber, the mouse, what is the mouse? What is the mouse? Yeah, that's the chamber. So the chamber is a cylinder, 5 liters. And there's a delay. And it's got 2 flat plates. On the side of the cylinder, it's got what you call that ground glass. So when the 2 plates are against it, it's gas tight. It's watertight, gas tight. And you got the arms closing it physically with a very strong strength. That chamber is equipped with an octode, an under-octode, 4330, which is measuring oxygen concentration every 3 minutes, whatever the state of the chamber. And also what you got on that device, you got an external octode to measure in situ oxygen concentration. So therefore, every time the chamber opens, you recalibrate or intercompare the 2 sensors. You show and to constrain the drift of each other, especially the one inside the chamber. And if you are deploying your instrument into the surface, you fit a PAR sensor, which is on the top of it, to measure up the light. So everything is run on an engine. And inside the titanium system, you got one for dedicated to the batteries, and the other one is with a computer. And that is a man-machine interface to collect the samples, the sensor information every 3 minutes. If you set it to 3 minutes, you can set it to 1 minute, whatever. And you set the framework of the deployment when it opens, when it closes. So the way it works, yeah. If it works. Okay, it's opening automatically, very gently. This process takes over a minute to open and close, to have very gentle movements, not have any breakage of any aggregates or whatever. And then it closes very tight. And then you can start your incubation. So depending if you deploy it in the surface water, basically you start the cycle before dawn. Okay, and then the chamber is closed and you measure up the cycle through the day. And you change the water for, you incubate for 23 hours and open again in the middle of the night to change the water sample. On the way the thing is deployed, the plates are like this when it's open, you've seen. So there is no settling into the chamber itself. And usually the way it's deployed on moorings, the water flow cleans up the chamber. So that is an illustration of the deployment in surface water. So you can see when it's open, you know, it's like a Carolina, theropod, Carolina, I think it is. And if you put it on this side, it's a multi with symbols. So what you got when you do a 24-hour deployment, when you first take the sample, you close the chamber, and then you get a linear drift, and that's your in situ respiration, measured by the respiration and the oxygen consumption inside the chamber. And then you switch on the light, so that's the light pattern taken from the PAR sensor, and you can see the sigmoid increasing the signal of oxygen, accumulating with the integration signal of the photosynthesis, minus the respiration. So this is a true measurement of dark respiration, or respiration in the night, and that's the true measurement in that period, the true measurement of net multiplication during the light phase. Okay, and then when you switch off the light, the sun is down, you measure respiration afterwards. So you've got advantages. You can measure respiration before the incubation and after the incubation to see if there's any bias, like DOC release during photosynthesis, fueling respiration, or inhibition from different reasons. So that you got light results. The advantage of that, you don't have to do any water manipulation because it's done in situ. You got high frequency resolution for your measurements, either respiration or photosynthesis. And when you deployed it, you can go and have a beer on the deck, rather than titrating samples. On the side, product you can have the relationship between the oxygen dynamics and the light. So you can derive from modeling different parameterization, which is very useful to understand the community response to light pressure. That's very useful. This is an illustration of iodine deployed in the deep sea. So that has been deployed at 2,000 meters. And every blue line you got here, it's a cycle of 5 days. Every 5 days, it opens for 3 hours and then closes for the remaining of the 5 days. On each of them, it's a drift from the oxygen octodes. So here it's now a year, so 50 around 50 cycles. And from each cycle, you derive a respiration value. So we do it for 5 days at 2,000 meters because the rates are low. So you need to integrate. And we decided to 5 days because we are looking at the noise signal ratio. And 5 days was the right time to incubate in order to go above the noise ratio with that kind of sensor. So better the sensor is, less drift you have, better your resolution are and your incubation can be. And that's the illustration of the derived rate of oxygen consumption at 2,000 meters, work for 5 years. And you can see you got variability, but it's pretty constant on 0.12 micrograms of oxygen per day. So that's the illustration. And that's the first time we were able to have a time series in a deep water for the respiration rate. Automatically, no titration. So that's a next generation tool.
Complementary tool. So the second tool we are using is the dual particle interceptor incubator respire. So this instrument has been developed by myself, but by Philippe Boyd and collaborators. Philippe is at the university, working at the University of Tasmania in Quebec. What the objective of this tool is to measure the mesopelagic respiration by particle-attached microbes. So it's complementary with the IODA, which is measuring, let's say, the bulk respiration. Here we focus only on particle-attached microbes. This instrument is working relatively well because, for one reason, it's a very simple instrument. It's a cylinder acting as a sediment trap. So here you have a cylinder made in titanium. At the entrance of this cylinder, you have a baffle. The role of this baffle is to stop the turbulence inside your trap. Then you have a sphere. I will explain a bit later what the role of this sphere. This sphere moved thanks to a motor here. And below the sphere, you have an incubation chamber, a 1.5 liter incubation chamber. Inside this chamber, you have an oxygen octode, an Ondera oxygen octode. So it's really simple, a few different parts. How it works, so usually we deployed, always we deploy this instrument on 3 to 15 mooring line for between 2 and 5 day deployments. And so far we have mainly focused on the upper mesopelagic, so between 100 and 400 meter depths. It can be I think this instrument can be deployed deeper, but we have decided to focus on the upper mesopelagic because it's where the flux attenuation is maximum. So it's a really interesting depth range. So when you deploy the instrument, so here it is an example. So here it's the oxygen time series measured by the opton inside the instrument. So you have two different steps. The first one is the particle collection phase. So in our example, it lasted 1.5 days. And this deployment lasted 60 hours. So you deploy the instrument, the particles settle in the trap, in the sediment trap, and eventually settle on this rotating sphere. Every 5 to 10 minutes, we have a rotation of this sphere, and the goal of this rotation is to transfer particles, sinking particles, into this incubation chamber, equipped with the optode. And the second goal of the second role of this sphere is to ensure that zooplankton and swimmers are not penetrating inside the chamber. And this is key because we really want to focus on microbes. And if we have zooplankton inside, the oxygen consumption signal will be, you can't exploit, you can't use it. And when the sphere is not rotating, the incubation chamber is isolating from the ambient water. So usually we collect particles for 1 to 3 days. The objective is to collect, to accumulate, pre-concentrate particles inside this incubation chamber. And we do that to be sure that we measure a signal in terms of oxygen consumption during the incubation phase. So then we switch in this incubation mode. So the sphere stops its rotation, isolating the chamber, this incubation chamber, from the ambient seawater. Then we follow the decrease in the soil oxygen concentration along this incubation phase, by the third. And at the end of the deployment, we have the oxygen consumption rates that we can convert to a carbon-based remineralization rate using a respiratory quotient. I will talk about it just after. And that's it. So now the last part of this talk is to illustrate how we can use how measure the oxygen consumption rates and link this rate with the carbon cycle. So here, so this is a plot from a paper recently published by Morten Eiderson. Just to illustrate that from this flux attenuation curve, so here I think it's the Martin flux profile. You can derive, you can estimate carbon-specific degradation rates in different layers of the water column. Using this, I won't detail this equation, but you have to assume a constant sinking velocity. And from this, from the flux, you can get, assuming a constant sinking velocity, you can get a concentration in carbon, in particulate organic carbon, and then you can get particulate organic carbon loss rates, and at the end, with this equation, you can get this carbon-specific degradation rates. So, what I want why I'm showing you this plot is that by doing this, we can get some very important, interesting insights. We can derive some degradation rates in different layers. So in this case, we get degradation rates ranging between 0.02 and 0.31 per day, depending on the layer. But we have very limited information about an insight into the relative importance of the different degradation processes that are occurring in these different layers and that are supposed to set this attenuation flux profile. So to get more insight and to try to estimate the microbial contribution of the POC flux attenuation, we can use the respire measurements. So if I will take this respire measurements as an example. But you have to make some assumption. The first one is that you need to convert your oxygen consumption rate into a carbon-specific mineralization rate, and for that you need a conversion factor. So what we call a respiratory quotient. And this metric is not easy to measure. So usually it depends on the type of organic matter that is oxidized. So here you have a table with different type of compounds and the corresponding respiratory quotient. And this plot comes from a paper published by Carol. So you have most of the RQ values that have been published. What I just want to illustrate is the range of the very large range of RQ values that have been measured. So when you assume a value, you make you add some uncertainties to your measurements. So usually most studies assume a RQ ranging between 0.8 and 1. And for instance, if we consider the phytoplankton cell, typically it's composed of 40% of protein, 40% of carbohydrates, 15% of lipid, and 5% of nucleic acid, and it gives us a RQ of about 0.9. So this is the first assumption. You need to assume a RQ. And to illustrate that, I just want to show you a recent studies trying to constrain the RQ, but in the mesopelagic, for mesopelagic particles. So this study takes place in the subantarctic and south of the polar front. We did deploy some sediment trap in the upper mesopelagic, so between 150 and 300 meter depth, collecting particles, and we use these particles, so without preservative, and we use these particles, these sinking particles, to do some in vitro incubation to measure the RQ. So here you have the RQ in what we call the lower epipelagic, so above 200 meter depth, and the RQ 100 meter below, what we call in the upper mesopelagic, between 250 and 300 meter depth. And what I want to show is how this major reduction in RQ between the lower epipelagic and the upper mesopelagic. So we have a reduction of about 60 to 75% over a depth range of only 100 meter depth. And once again, for most study, we have to assume a constant RQ spatially, but as well over depth in the water column. And this is a major uncertainty of our measurements. The second step to estimate this microbial contribution of the POC flux attenuation, you need to convert this carbon-specific remineralization rates measured in situ to a flux attenuation. So in other words, you need to convert POC loss per day in the POC loss per meter in the water column. So you need sinking velocities. And this is another parameter that is not easy to measure, especially in situ. This study reported like all available sinking velocity measurements made in situ and in the lab. So you have the sinking velocity as a function of the size, of the diameter of the particles. Just two things here, two key messages. We observe a 3 order of magnitude range of sinking velocity. And there is no relationship, no clear relationship between the sinking velocity and the diameter of the particle. So at some point, you will have to assume sinking velocity, probably from the size of the particle, but keep in mind that you introduce some uncertainties as well. So now that we know the different steps and the uncertainties, just to illustrate you can do with the respire, for instance. So if we go back to this flux attenuation curve, this Martin curve, basically they are driven by three main processes. So the microbial mineralization, what we measure, the zooplankton flux feeding, particle fragmentation, and as well the vertical mineralization that can inject particles at depth. With our method, with our in-situ incubator, we can measure one of these three processes, so the microbial mineralization. We have done that in the upper mesopelagic between 100 and 300 meter depths, in different areas of the ocean, quite contrasting oceanic regions, so in the HLLC region, in oligotrophic regime and productive regime. And what I want to show you is that we got some carbon-specific remineralization rates. So that range between 0.08 and 0.23 per day. This is the median rate for each area. These rates, we got them by assuming a fixed RQ. From these rates, we can get, assuming a constant sinking velocity over the depth range considered, we can estimate the contribution of the microbes to the flux attenuation. So we get a contribution ranging between 7 and 30% in the upper mesopelagic. This is important. And one of the conclusions of this study is that in the upper mesopelagic, zooplankton are a key player, key degrader of the flux. But deeper in the water column, the microbes start to play, even if in the upper mesopelagic, they play an important role. And deeper in the water column, they play much more important. So it was an illustration of how we can get insights about into the contribution of microbes to the carbon flux attenuation. That's it. Yeah.
That was excellent. Thank you so much.